So I will start now. So in the last lecture of mine, I arrived at the point that okay, you are there, that I will speak about orientation. So today, the title is orientation. And let's start by the quote of the day. Every orientation presupposes a disorientation. Okay, this was for today. First of all, I would like to show you a nice theorem, the orientation theorem of Hakimi, which is about nothing to do with connectivity, just the in-degree constraint orientation problem. But we will see it still, it's something very simple. For the proof, I can show you again the uncrossing technique, so you will learn really well this technique. And then it already contains some nice problems. So I will show you some applications as well. And then I will start with my problems about connectivity. And the main topic today, this will be the well-balanced orientation theorem of Nash-Williams. Okay, so the first thing, some small definitions. If you have a graph, a directed graph G, and M is a vector on the vertex set, and let's say it's non-negative integers, I will say that this vector is the in-degree vector of this directed graph. M is the in-degree vector of G if, I hope you can imagine what it means, for every vertex, the in-degree of the vertex is exactly this value, M of V. So this is the definition of in-degree vector. Okay, then clearly I will use the notation M of x. So this is a vector, but I can use it as a set function, just like a modular function. So notation, simply M of x is the sum of the M values inside x. And just more remark before the theorem. If M is the in-degree vector of a graph, directed graph G, then this value M of x minus I of x, you should tell me what it means. What is this? So this is the sum of the in-degrees of the vertices inside. In this, we have this vector. For each edge, we have either. Okay, it's there. And there are the arcs entering as well. It's counted here, and nothing else. So this is the in-degree of the vertex x. Okay, so this will be very important. I will give you a remark about this in-degree vector, in-degree function, and so on and so on. This is very important. So the theorem is the following. We are given an undirected graph E and vector M, non-negative on the vertex set. There exists an M orientation, which means that this is the in-degree vector. I of x, I defined in the first talk, this is the number of edges in the subgraph defined by the vertex at x. Okay, so there exists an M orientation G. Okay, if and only if, and there are two conditions. First of all, if we have this orientation directed graph, then M of x minus I of x, it's this, and this is non-negative. So So this will be the first condition. M of x is at least I of x for each vertex at x. And there's a second one, almost the same. If we use this for the vertex set V, then this minus this is equal to this, which is 0. So clearly, M of V must be the number of edges. So here is the theorem. And now I will prove it. How one can prove something like this? In fact, for this theorem, there are lots of proofs. I will show you some of them. First of all, one using the uncrossing technique. So how to prove it? Proof. The idea is the following. Well, the idea is very, very simple, induction. Induction on the number of edges. If this is 0, there is nothing to prove. Then you can forget it. So this is the base. It's okay. Well, let's see what shall we do. If this is not 0, then this means that M of V is strictly positive. So there exists at least one vertex with strictly positive value. So we will take a vertex S such that M of S is strictly positive. And the idea is that we take an edge incident to this vertex, we delete this edge, we decrease the M value of this vertex, and then maybe we are lucky. And then the graph and the new vector M prime will satisfy the condition. By induction, there exists an M prime orientation. We put back this edge, it looks like Vs, so it will increase the in degree of S. So this will be an M orientation of the graph G. So this is the idea. So, for at this moment, I don't say anything about this edge Vs. We will have to choose in a good way to such that it works. So at this moment, it's an arbitrary edge. For Vs, let's define G prime by G minus Vs, and M prime, as I told you, on S we divide by 1. No, we decrease by 1 if V is S, and otherwise it will be the same. And I don't know whether I should repeat or not. If this graph and this vector satisfy the condition, then by induction we are done. If G prime and M prime satisfy the condition, then by induction, still I will repeat, by induction, there exists an M prime orientation, G prime oriented of G prime, and then by adding this edge plus Vs in this direction, this will be an M orientation of the graph. We are done. So the question is how to choose this edge so that this condition be satisfied. So what does it mean? What does it mean that this condition is not satisfied? I hope that you see it. So don't forget what we did. We decreased the M value just for one vertex. Before, it was inequality in this direction. And now, we decreased this, and it became strict inequality in the other direction. So this means three things. If and only if there was a tight set with equality. There exists a tight set m of x equal to e of x, such that, and what else do we know? It was equality. Now it's strict inequality, so this is decreased, so S is inside. S is unique, x. And on the other hand, this side didn't decrease. So this means that this edge is not in this set, which means V is outside. So we have to choose this edge, Vs, in such a way that we don't have this. So now you see that tight sets play a role. Okay, and then we see that we are done if we can prove two small claims. We are done if we can prove that the intersection of intersecting tight set is tight, then it will help us. Intersection of intersecting tight sets is tight. And then the second, first of all, if we know this, then if we consider all the tight sets containing this vertex, then there's the smallest one. It's at the end, it is unique. Okay? So what we want to prove that there is an edge inside this smallest one. And then we are done. There exists the unique smallest tight set containing S contains an edge Vs. And if we can prove this, then we are done. But first of all, maybe a little bit I was cheating. I said that there's a unique smallest tight set containing S. Why is it true? To have a smallest one, we need at least one tight set containing S. Fortunately, V is tight. So there is one tight set, so there's the smallest one. And then, if we can find such an edge, Vs, then we know that every tight set containing S will contain the smallest tight set, so it will contain this vertex V, so the edge Vs. Which means that we cannot have this problem, and then it will work with this edge Vs. So we have to prove only these two things, and it will be easy. I hope you see everything. So for the first one, it is in fact the same proof as you have already seen. If x and y are tight and the intersection is not empty, in fact we don't need this, but anyhow I will use in such a way that all of them will contain S, and intersection is not empty, then the intersection is tight. So, proof. I'm almost sure that everybody can tell me what I have to write. So we use that these are tight sets. M of x plus M of y is I of x plus I of y. It's okay. This is, surely everybody remembers that this is supermodular. So this is I of x intersection y plus I of x union y. And then we know somewhere the condition I. This M covers this function. So this is less or equal to M of intersection plus union And then this set function, this is modular. So this is the same, but m of x plus m of y. Since this is a vector m, so this is modular. And then we have equality everywhere. And here we have equality, here we have equality. In fact, it's not important for us now. So we have equality here, and that's good. Okay, this is the first one. Second one. I have the smallest tight set X. I have a vertex S inside, my vertex S. And I have to prove, I would like to show that there is an edge inside incident to S. So suppose that there is nothing here. So what happens if we delete this vertex from X? It was tight. So we had equality. And now what about this set? This is strictly positive. I deleted, so this is less. What can I write here? Don't forget there are no edges here. So if I delete this vertex, I didn't delete any edge. This is somehow a problem. We have the other way around. And now be careful, just a small technical problem. It's not true what I said. So where is the problem? Yes, it is possible that there is nothing here. And how is it possible? Don't forget that it was a tight set. So this one means that there was a loop. And in this case, we can use this loop. Okay, so in fact, you have to say, first of all, check if there is a loop on S. Then in this case, this edge is okay for us because it works everything as we want. And then if there is no loop, then it's correct what I said, because it's impossible that this is a singleton. Okay? So I don't write down this small technicality, but you have to be careful always. Okay. I proved everything. So this was another proof using the uncrossing technique. And now some applications. Before the applications, just some words. How should I explain it? So in fact, there's another proof for this. Simply, if you take an arbitrary orientation, and then you can improve this orientation by reorienting passes from bad vertex to a bad vertex. So if you take second proof, I just show you how it should work, and you can do it if you want. Second proof. So take an arbitrary orientation, and then you look at the vertices where rho is too small, strictly negative. It's not big enough. This is a small vertex. So there are small vertices here. This is the big set S. Then there are some big vertices. Okay, big vertices, which means that R of u is bigger than M of u. And here, it's okay. It's already as we want. So rho is M. And then what you have to show that there is a path like this. And then you reorient this path. And then here it will be much better, one better. Here it will be one better. And otherwise, it doesn't change. And then you continue. And to find this path, you have to use the condition. Okay, so this was a second proof. Let's say I didn't work it out. The third proof, in fact, this problem is nothing else, just flow. So this is a special case of flows. Simply, if you look at this, and then you add a new vertex, S, so an arbitrary orientation. You take here m of v minus rho of v arcs everywhere. So this is this. Here you add t, here you add these arcs, which is rho minus m. And then what you have to find simply a flow from S to T. The capacities are 1 everywhere. Which value the sum of all of these values. And then you have such a big flow. There is one which is integer because the capacities are integer. And then you can decompose it into passes from S to T and circuits. And you can reorient all of the passes. And then it will exactly as we want. All the indices. Okay, so this was the third proof, let's say. And then you can say that, okay, it's just a special case. So it's a nice proof, short proof, it's okay. But still, it has some nice applications. So let's show you some applications. The first one, you will say that it's a triviality, but still, it's an application. If you are looking for an Eulerian orientation, and in fact, in this talk, Eulerian for me means always just if it's directed, in degree equals out degree, and if it's undirected, then every vertex is of degree even. The connectedness, I don't care about it. Okay, Eulerian orientation, you know what to do. If you want to find an Eulerian orientation, how to write it as an M orientation, simply you have to define MV as the degree divided by 2 for every vertex. And then it will be an Eulerian orientation. Okay, second, which is slightly more general, and I am not sure that everybody knows this. It's a nice result about mixed graphs. Eulerian orientation of mixed graphs. What does it mean, mixed graph? This is something like this. Vertex set V, we have an edge set, and we have also an arc set. So some of the edges are there, and some of the rest are already the arcs. So somebody, let's say, has started to orient our graphs, and we have to finish it to be an Eulerian orientation. And now, again, you can write down how to define M. At the end, the in degree must be without orientation, the degree divided by 2. So this is degree in E plus rho plus delta. So without orientation, this is the degree divided by 2. But we have already rho of V arcs entering. That's it. Third one, perfect matchings in bipartite graphs. And in fact, this trick was already mentioned by Kazuo. So if we have a bipartite graph UW, and we have, let's say, a perfect matching, then what to do? Simply we can orient the perfect matching in this direction, and all the other edges in the other direction. Let's say there are lots of them, I don't know. Okay, and then we know all the in degrees. Here the in degrees are 1. And in the other part, there is just one arc leaving, so all the others are entering. So this is the degree minus 1. And if you have such an orientation, it provides a perfect matching. Okay, this is still something simple. You can say, fourth one, a generalization of this, F factors in bipartite matchings. In bipartite graphs. Bipartite graphs. Well, I'm not sure that you know what an F factor is. So let's see. F factor, maybe I will write it here. So F is a vector on the vertex set, non-negative. And then an F factor is an edge set, like a matching. A matching is a 1 factor. For each vertex, the degree is exactly 1. So F factor is an edge set such that the degree in F of every vertex is exactly the value written on that vertex. Okay, so this is a F factor. And then again, if you have an F factor, something like this, then you can orient all of the edges in this direction, all the edges in the other direction, and you know all the integers. So you see that what you have to do is simply M of u, F of u for each vertex in u, and M of w is simply the degree minus F of w. Okay, and the first exercise for today, simply prove the corresponding theorems using Hakimi's theorem. So the problem is that I don't know whether you know all of these theorems or not. Should I mention the theorems, or you can? I see one like this, or the other is like this, or you can find them in the books, or the problem is that I don't have so much time. So anyhow, I write somehow just this exercise, show the corresponding theorems using Hakimi's theorem. The first two is really trivial. For the second two, you have to work a little bit. They are not so trivial. Okay, so I think this is what I wanted to tell you about M orientation. And now orientations with connectivity requirements, but first I have to work. I think it will work like this. Okay, so what do I have to do? Aha. To introduce this problem, I wrote a short story, which is short, and I will read it. Maybe you check the materials that I give on the web page, but if you didn't check it, now I will read this short story. So it will introduce the problems that we will work on today. Mr. Orient, why not? The mayor of the city called the edges, you can imagine why, having wanted to make the main street a one-way street, but unfortunately made a mistake by ordering the one-way sign and received 100 signs, as many as the number of the streets in the city. You understand what it means. To be justified, he decides to use all the signs, well, he's a politician, that is to make all the streets of the city one way. Having finished his plan, he realizes that it doesn't enable him to go home. It's a problem. He thus goes back to work while keeping in mind that he must be able from the city hall to reach any point of the city. After one moment of reflection, he realizes that he must be able from any point of the city to reach all the others. Being proud of him, he presents his project to his assistant, a well-balanced man, who reminds him that during summer, some streets of the city may be blocked by floods. They thus try to conceive a plan where blocking any street doesn't make a district inaccessible. But they are still not satisfied. Examining their plan, they see that there are far too many passes from the downtown to the shopping center and not enough in the other direction. They try an ultimate improvement to place the one-way signs so that the orientation of the streets be well balanced. Since then, the city was renamed the Arcs. So this was the story, and I hope that you recognize all the problems inside. So I will write down the problems. The first problem, clearly, everybody imagine what happens here. This is a city. The streets are the edges of the graph. This is an undirected graph. He had as many one-way sign as the number of streets of the city. So what he wants simply direct the graph. So each edge must be replaced by a direction, either this direction or that direction. So the first problem, when we decided this, just an orientation. So this is just for children, not for us. The second problem was he must be able to go home. So this means route connected. From a given vertex, pass for all the others. Route connected. Or more generally, you can imagine K route connected, which means that for a given vertex, to every other vertex, K arc disjoint passes. K route connected. This wasn't mentioned in the story, but you can imagine this problem as well. Then it was this strongly connected from anywhere. He must be able to go anywhere. So the third one was strongly connected. The fourth one, blocking a street. There is no district inaccessible, which means after deleting an arc, it's still strongly connected. So this is two arc connected. You can imagine more generally K arc connected. And finally, it was the last one was the well-balanced orientation. Okay, so this one, as I mentioned, is for children, not for us. We don't check it. Route connected, well, I hope that I make like this, I sign like this. Everybody knows there is an orientation which is route connected if and only if the graph is connected. There's a spanning tree, you can orient it such a to be an arborescence, and it's okay. K-rooted connected, well, it's already a theorem, so I will mention here, due to András Frank. So we have a graph, undirected, and we want to decide whether there exists a K-rooted connected orientation. Maybe I will write here the definition. So in the directed graph, from S, for every vertex, there are at least K arc disjoint passes. Okay, so there exists K arc, no, not K arc connect, K root connected orientation, if and only if. And now the condition is not so trivial. So this is not just a cut type condition, it's a partition type condition. So if you consider a partition, maybe I will show it here. This is the vertex set. You consider a partition, and your vertex S is here somewhere, and we suppose that there is a K root connected orientation. Then here there will be at least K arc entering. For this one as well, there will be at least K arc entering. For this one as well, there will be K arc entering. For this one, we don't know anything. So which means if you add the integer of this set, 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 which is exactly the number of edges between the different members of the partition, is at least K times P minus 1, where P is the number of the partitions. The number of the members of the partition. So E of P, so this is the number of edges between Vi, Vj in the partition. So all the Vi, Vj, so all the edges here, these crossing edges. This must be at least K times P minus 1. And maybe I don't say anything more about this. I wanted to say something, but now I'm afraid that I don't have time. And then, so just some words about this result. In fact, if you want to prove this result, not a direct proof, but using other theorems, then you can do it. So if you know the packing theorem of Nash-Williams about spanning trees, this is nothing else than there exists K edge disjoint spanning trees. And then you can orient in such a way that you have K arc disjoint spanning arborescences, and then you have the passes. But in fact, what András Frank had in mind, he wanted to prove Nash-Williams theorem using his orientation theorem and Edmond's arborescence packing theorem. So there is a result, something like this. There exists in a directed graph K arc disjoint arborescences, if and only for each vertex set not containing the root, there are at least K arcs entering. So this is Edmond's arborescence packing theorem. And then the idea of Frank was simply using his orientation plus Edmond's directed version packing arborescences, then it implies, I didn't write here Nash-Williams. It implies Nash-Williams theorem, which is this result. And I have to mention that this is just a simple, very simple idea. If you want to prove something for an undirected graph, what you do, you try to find the corresponding directed problem, you prove it, and then you prove an orientation problem, you put them together, and poof, you have a solution for the undirected one. So for example, some years ago, I made with my students the same thing. There was a new result about packing spanning trees with some matroid properties, additional matroid properties, rooted spanning trees. This was in fact a result of Shinichi Tanigawa, who was here but he had to left. And then with my two students, we proved the directed version. And then we have found somewhere that András Frank, he has proven very, very general orientation theorem. So that orientation theorem or directed version implied the undirected one. And the new proof became much simpler than the original one. So this is just a simple idea, but sometimes it can help a lot. Okay, this one is done, this one is done, this one is done, this one is done. This is Nash-Williams weak orientation theorem we have already seen. Okay? We are almost at the well-balanced orientation theorem, but before I started with M orientation, now I spoke about orientation with connectivity results. Now let's put them together, and there you can find something there as well. So this is a theorem of, again, Frank, but maybe it's just a remark. So if we are looking for an M orientation that is K arc-connected, let's say, or K root connected. So given an undirected graph G and the vector M non-negative on the vertex set, there exists orientation, an M orientation that is, and in fact I will write two theorems together. That is, in the first one, K root connected, if and only if, and the condition is the following: M of x minus I of x must be at least K if the vertex set is in V minus S, and at least 0 if x contains S. And the other theorem, K arc-connected, if and only if M of x is minus F of x is at least K for every vertex set with X non-empty. And again, I will explain to you something very simple, but I would say magical. So let's see, I will concentrate just on this one, because it's easier to speak on this one. I don't have to speak something like this. So suppose that we have an M which satisfies this condition, and of course I forgot something. In both we need this condition that M of V is the number of edges. Maybe I will add here M of V is equal to E. So let's suppose that we have this condition plus this condition. Then we know that this minus this is at least K, so at least 0. So by Hakimi's theorem, there exists an M orientation. And here comes the magical part. You take any M orientation, and automatically it will be K arc-connected. Because we know this. And why? Because this we have seen at the beginning. It's not there anymore. This is simply the in degree. And if the in degree is at least K, this is K arc-connected. So this is the magical part. Automatically, it will be K arc-connected. So here what I wanted to explain about M orientation and connectivity is the following. If you know just the in degree vector, then because of this, it characterizes the in degree function, and the in degree function tells us everything about the arc-connectivity. So simply knowing the in degree vector, we know everything about the arc-connectivity of this graph. So again, this is something magical for me. When I first learned this from András, I said, wow, it was really strange. But this is true. Okay. This was the first part, and the second part is well-balanced orientation. But first, I have to work. No, not there, maybe here. well balanced. This is a keynote, a key word. So somewhere I have a quote about this. The universe is so well balanced that the mere fact that you have a problem also serves as a sign that there is a solution. Well-balanced orientation. This is the last part of this talk. Well-balanced today. First of all, just an exercise and then the definition. I like this exercise because it's simple. You think that it's trivial, and still you have to use something. So it's not trivial. What is it? You have an Eulerian graph. G is Eulerian. An orientation is Eulerian. If and only if. Well, this is about local arc-connectivities and edge connectivities. The local arc-connectivity from U to V is exactly half of the local edge connectivity for each ordered pair. So I am sure that you see one direction is trivial. This direction is trivial. If it's Eulerian, really 1 minute, half a minute, you see that it's exactly half. But the other direction, you have to work a little bit. In fact, if you have to use something. Okay, so here is the definition of well-balanced. If you have a graph, you want to orient it, the best what you can imagine, what it is, half of the local edge connectivity before. This is the best that you can imagine. So an orientation is well-balanced if and only if the local edge connectivity in the directed graph is at least half of the local edge connectivity before, and then this cannot be done, of course. This is the integer part for every UV direct ordered pair. So this is the definition of a well-balanced orientation. At least half of it. So somehow the number of passes from U to V and more or less is the same as the number of passes from V to U, and this number is big enough, the biggest possible. And the theorem of Nash-Williams. So attention please, Nash-Williams, this is not Nash plus Williams, this is Nash-Williams. Okay? It's a little bit shocking, but every graph has a well-balanced orientation. So sometimes for K arc-connectivity, one say that this is the weak orientation theorem of Nash-Williams, and then we say that this is the strong orientation theorem of Nash-Williams. What I wanted to say, oh yes, I almost forgot it. Yes, maybe just a small exercise here. This is equivalent rho of x minus delta of x is at most, if you don't want to do this, it's not so important, but this is, in fact, one works with this. When one wants to prove something, you have to translate it into inequalities and so on, into cuts and so on. So you have to work like this. This is at most the degree in the graph G minus, and there is something, an R function where R of x is the maximum of the lambda G U V U in X, V not in X. So for each vertex at X, you take the maximum local edge connectivity. This is R of X. And then orientation is well balanced if and only you have this inequality. So this is a simple exercise, really simple, but not so funny. Okay, small remark here. Of course, the strong orientation theorem of Nash-Williams implies the weak orientation theorem. And maybe I should. The problem is that here I write for me well-balanced orientation theorem because later I want to tell you others. But usually one says that this is the strong orientation theorem. But still, I would like to call it well-balanced orientation. Well-balanced orientation. Oh, sorry. Should I prove this, or you can imagine? I think you can imagine this. Okay. Nash-Williams didn't prove this one. He proved something stronger. This is the strong theorem that he proved something stronger. In fact, for the Eulerian case, a well-balanced orientation was an Eulerian orientation. Here, if there are odd degree vertices, clearly you cannot have an Eulerian orientation, but maybe you can have a semi-Eulerian orientation, or what I call smooth orientation, in degree minus out degree for each vertex is at most 1, so the difference between them is at most 1. And then if there is such an orientation, so here are T of G, this is the set of odd degree vertices. And suppose that we have this orientation, which is smooth. Then there are some vertices where this rho minus delta is -1, and there are some with +1. For the others, is 0. And then you can add rho minus delta is negative, so this is too big. So I have to add something like this. Then we can add something like this and orient in M, and then this will be Eulerian. So in fact, instead of saying there exists a smooth, well-balanced orientation, I will say that there exists a pairing M of the odd degree vertices in such a way that there exists an Eulerian orientation of G plus M, such that G will be well-balanced. So this will be the smooth, well-balanced orientation theorem. Again, Nash-Williams, smooth, well-balanced orientation theorem. Oh, I should have wrote this by red. So there exists a pairing. Maybe I should explain why I use this word pairing. So you see this M is something like a matching, a perfect matching on T of G, but this is not an edge set in the graph. It's nothing to do with the edge set. So it's some new edges. So this is why I use this word pairing instead of matching, perfect matching. So there exists a pairing M of T of G such that there exists an Eulerian orientation M plus G so that G is well balanced. So this is the theorem. So you see it's the same that smooth well balanced orientation. I just use this word pairing. Okay, so this was, maybe I will write some numbers because I will continue. This was the first one, this is the second one. And in fact, Nash-Williams, he didn't prove this one. He proved something even stronger. So I will write down now this stronger version. The two. Well, of course. There exists something such that G is well balanced. There exists a well balanced orientation. Okay, third one. Theorem of Nash-Williams. It will be stronger because I will change this for every. So maybe again this color, it's very useful. Here it was there exists a pairing such that there exists an Eulerian orientation. And now in this I will say that this is the strong pairing theorem. No, this is red. Strong pairing, which is the following. There exists a pairing of TG such that for every Eulerian orientation, for every Eulerian orientation, G is well balanced. This is stronger. And I continue. He didn't prove this one. He proved something even stronger. I will write it down here. Theorem, Nash-Williams. This is the feasible pairing theorem. This was 3. This will be 4. Feasible pairing. So what it says, there exists a pairing M of TG such that, first of all, here we said that for every Eulerian, maybe this will be 2, and this will be 2 the same. So I will write here for every Eulerian orientation, G is well balanced. But there is something more. We don't know anything about the orientation of M. And in fact, you can start as you want. Every orientation, for every orientation of M, every orientation like this, there exists an Eulerian orientation of G plus M. So this is more. Here I said something something about if we have an Eulerian orientation, that this is well balanced. And of course there are Eulerian orientations, but it's not here, you cannot know that you can start this orientation as you want for M. So this is even stronger. And now I continue. Okay, I don't say that this is not the theorem that he proved. This is what he proved, but not in this form. This is an exercise for you. What he proved is the following. There exists a pairing M of TG such that the degree of M of every vertex set is at most, and this is exactly what is here. For every x. So, this is what he proved, but if you want to use this result, you have to use this way. Okay? You cannot use something like this. You don't understand anything of this. But this, you can use it. And now I will show you some applications using this result. Okay. I would like to say applications. If you check this list, then you can imagine another type of theorem. For every pairing, there exists an Eulerian orientation such that G is well balanced. Is it true or not? This is true. So when we learned this, in fact, we generated some theorems using this last one. And this will be this list here. So theorem of Zoltán and myself for every pairing. There exists Eulerian orientation. Such that G is well balanced. At the end of this list, I will tell you exercise, prove all of them. Okay, so maybe you can sign at once. Prove this using one of these results. You can choose what you want. You choose that one that you have to use. And then this one is a triviality using something like this. Okay. The next one. So this will be something about simultaneous well-balanced orientation. In fact, all of them in this list. Theorem again with Zoltán. If you have an Eulerian graph, then there exists an Eulerian orientation of this graph such that for every vertex V, if you delete this vertex, what you have is a well-balanced orientation of the remaining graph. So this seems to be something very, very strong, but I have to admit that using this is just a triviality. On the other hand, there is a corollary of this, which was a theorem, an earlier theorem of Berg and Jordan. And it said the following: if you have an Eulerian graph, it has a two-vertex connected orientation if and only if G minus V is 2H connected for every vertex V. Connected for every vertex. I don't want to explain why this implies this. Everybody must see it. Okay, next one. Theorem of Nash-Williams. It was a theorem. He proposed this theorem. He never provided a proof for that, but clearly he knew it. So this is a theorem of Nash-Williams. And in fact, we started all of this because of this theorem, because we wanted to prove it. If you have a subgraph, if H is a subgraph of G, then there exists a well-balanced orientation of G such that this subgraph in the directed graph will be a well-balanced orientation of that subgraph. There exists G well-balanced such that G, how should I? Maybe I will write this way. So you look at this subgraph GH, and this is in this orientation is also well-balanced. So it's simultaneously well-balanced for the graph G and the subgraph H as well. And in fact, we generalize this theorem as follows. There exists, we are given a partition of the H set. Then there exists a well-balanced orientation such that it is simultaneously well-balanced for all of these subgraphs. And you see that this one implies this one. If you take H and the complementaire, then you will have it. And again, the proof, very, very simple. You have to play a little bit with Eulerian graphs defined by pairings, and then you will have this. And using this one of these results. And then, since we were playing with these things, we found another result for vertex partition. If V1, Vk partition of V of G, then there exists a well-balanced orientation such that, well, maybe I should show it here somehow. So we have something like this, V1, V2, V3, V4, a partition of the vertex set. We have some edges between them, I don't know how. 1, 2, maybe other this way, something like this. And then if we contract for every Vi which is outside, so for example for this one we get this, for the other one we get 1, 2, 3, this, so this is V1, V2, this is V3, 4. This is V2, for this is degree 2, and for this one 1, 2, 3, 1, 2, 3. And if you contract all of them, so here we have 1, 1, 1 here, 1 here, and 1 here. So here I contracted this, I contracted this, I contracted this, I contracted this, I get this one. So there is a well-balanced orientation such that it provides well-balanced orientations for all of these graphs. So G contracted V minus Vi for every I, and G contracted V1, V2, and so on, Vk. All of these graphs are well balanced. Okay, so as I promised to you, exercise, prove all of them using that and just playing with these Eulerian graphs. And since still I have some minutes, I will say some words about vertex connected orientations. Hey, oh. Shit. No, I don't do it. Okay, so vertex connected orientation. So for a long time it was an open problem, and recently it was completely settled. So for k equals 2, it's a theorem of Thomassen. G has a two-vertex connected orientation if and only if the graph is 4-edge connected and the graph minus V is 2-edge connected for every vertex. So you see when I mentioned this result, this was the same for Eulerian graphs. So before it was known just for Eulerian graphs, and then last year or 2 years ago it was proved by Thomassen. It's a complicated induction proof. I didn't understand anything. This is the proof, and I would like to understand. So please, if you can find a simple proof of this, just write an email for me. I would like to read it. Okay, so for k equals 2, it's done. And for k at least 3, this is a theorem of Durand de Gervigny. Who was my former PhD student. K at least 2, 3. The decision problem, whether there exists a k-vertex connected orientation, is NP complete. Decide whether G has a k-vertex connected orientation is NP complete. So you see, more or less it's settled. For 2, it's okay. Bigger than 2, larger than 2, it's not okay at all. It's too complicated. And I think